Welcome. In this session, I will discuss how to find limits of rational functions at infinity and negative infinity. The idea is somewhat similar to what we did when we had 0 over 0. We tried to factor and simplify, hopefully cancelling out the factor that goes to 0. Here we want to somehow get rid of factor that goes to infinity. But that factor is the power of x, the highest power of x that occurs, and we cannot usually factor it in the usual sense. But we can pull it out by dividing by that as well to compensate. So it will be easier to understand if I actually do an example. Let's first do an example where we have the same highest power in the numerator and denominator. This is the limit as x approaches infinity of 2x squared plus x plus 3 divided by 3 plus 2x minus x squared. So the numerator, the highest power is x. I want to pull that out. To compensate, I need to divide by x squared. We'll do this inside the parenthesis and also distribute the division by x squared. So I'm dividing each term by x squared, giving me 2x squared over x squared plus x over x squared plus 3 over x squared. I'm going to do the same thing for the denominator. The highest power is x squared. I pull that out. And to compensate, I divide each term by x squared. Now we are going to simplify this. X squared over x squared is 1. And we simplify the rest of the small fractions. 2x squared over x squared is 2. And then plus x over x squared, that's plus 1 over x. Then plus 3 over x squared. The denominator I have 3 over x squared plus 2x over x squared is 2 over x. And minus x squared over x squared is negative 1. Now each term here is either a number or reciprocal of a positive power of x. So the limit is either the number, the constant, or 0. So now we have a regular number as the limit, and so that's the limit of the original function. What if numerator and denominator don't have the highest power of the same degree? Let's first do one where the numerator has smaller degree. The first step is still the same. Pull out the highest power of x in the numerator and the denominator eventually. And to compensate, divide each term by the power of x that we pulled out. So numerator I pulled out an x, I have x over x plus 3 over x. The denominator I pull out an x squared, then I will have x squared over x squared plus 4 over x squared. Now I'm going to split it up into two factors. One factor consisting of just the powers of x I pulled out, the other factor consisting of the small fractions. So the first factor is x over x squared, the other factor consists of the rest of it. X over x squared is 1 over x, and these fractions simplify the same way in the last example, and I will get either a constant or number times reciprocal of a positive power of x. So if I actually do the simplification, then the first factor I have 1 over x, so I can do its limit. Second factor I have 1 plus 3 over x plus 1 plus 4 over x squared. Now in the second factor, as I said, each term is either a constant or reciprocal of a positive power of x which has limit 0. In the first factor I have 1 over x, its limit is also 0. So I get 0 times 1 plus 0 over 1 plus 0. Again, this is a regular number, so its value is the limit of the original function. Finally, we look at the case where the numerator has larger degree. The first two steps run, say, similar to the previous example. The numerator will pull out x squared, giving me x squared times 2x squared over x squared plus x over x squared. The denominator will pull out an x, giving me x times 3 over x minus 2x over x. Again, I'm going to split it up into two factors. First being x squared over x. The second is the rest of it. X squared over x is x. And then the second factor is 2 plus x over x squared is plus 1 over x. The denominator I have 3 over x minus 2x over x is minus 2. Again, in the second factor, each term is either a constant or reciprocal of a positive power of x. So the limits are all just ordinary numbers. In the first factor, though, I have a positive power of x and I have to look at its limit. Its limit, the factor is x, its limit as x goes to infinity is infinity. So I get infinity times something. Let's see what that something is. The limit will be 2 plus 0 over 0 minus 2. Note that this is a non-zero number, which is good, because if you had infinity times 0, you would be stuck. But infinity times a non-zero number is infinite. It's simply a question of whether it's infinity or negative infinity. This number is 2 over negative 2 or negative 1, so we get negative infinity. Before we stop, let's look at some common patterns. In all three examples, we had a limit of a function in which the numerator and denominator all had terms, one of which was a constant. Every other term was reciprocal of a positive power of x, which has limit 0 at both infinity and negative infinity. Which means limits of expressions like this or this or this, will be some non-zero number given by the two non-zero numbers in the original expression. If the numerator and denominator had the same degree, then this is the only factor, and that is the limit. But if the numerator has smaller degree, we have another factor which is reciprocal of a positive power of x, so we get 0 times some regular number, the limit is 0. But if the numerator has the larger degree, then I get this non-zero number multiplied by limit of a positive power of x, and that could be infinity or negative infinity depending upon which combination we have, and then we might get positive or negative from this factor. So in the combination, in the product, I will get infinity, but positive or negative depends upon the actual numbers. But this is the general idea. Note that the limit depends upon two things. One is the ratio of the highest degree powers. The other is the ratio of the coefficients, which determines which number I get if the numerator and denominator have the same degree, and which sign I get if numerator has larger degree. We can use these observations to come up with a shortcut method, which I will describe next time. I will stop here for now. Bye.